On behalf of the Harvard Club of Southern California, Herman and I would like to welcome you to the Myron Kayton Science Pub number 19, From the Possibility to the Certainty of a Supermassive Black Hole. My name is Ethel Lachko, Board Director of the Harvard Club of Southern California and founder of the Science Pub series. And together with Herman Enciso, Professor of Mathematics at UCI and Board Director of the club, we facilitate these amazing presentations. The Science Pubs were created for the purpose of offering our members a casual forum to discuss STEM current events in an interactive setting. Please do not hesitate to contact us if you have any suggestions for topics or if you wish to share your expertise with us. This time, we would like to thank Florence Lynn, mathematician, member of our club, and a strong supporter of our Science Pubs for bringing Dr. Ghez accomplishments to our attention. I would also like to take the opportunity to welcome and thank our affiliates. MIT Club of Southern California, thanks Anu. Phi Beta Kappa Honor Society alumni in Southern California, thanks Joan. The Alumni Network for Harvard Women, thanks Kay and Florence, and our friends from Carnegie Observatories, John and Erica. I would also like to welcome our very special guest speaker this afternoon, the 2020 Nobel Laureate in Physics, Andrea Ghez, Director of the UCLA Galactic Center Group. Thank you so much, Dr. Ghez, for being with us this afternoon. After Dr. Gez's presentation, Herman will moderate the question and A session. You are encouraged to write your questions on the chat at any time. Without further ado, it is my honor, my great honor, to introduce you to our amazing speaker this afternoon. Andrea Ghez, Professor of Physics and Astronomy and Laurie B. Lichtman and Arthur E. Levine Chair in Astrophysics, is one of the world's leading experts in observational astrophysics and heads UCLA's Galactic Center Group. Dr. Ghez is best known for her groundbreaking work on the center of our galaxy, which has led to the best evidence to date for the existence of supermassive black holes. Andrea has received numerous honors and awards, including the Nobel Prize in 2020, when she became the fourth woman to be awarded the Nobel Prize in Physics, sharing one half of the prize with Reinhard Genzel and the other half of the prize being awarded to Roger Penrose. The Nobel Prize was awarded to Ghez and Genzel for their independent discovery of a supermassive compact object now generally recognized to be a black hole in the Milky Way's galactic center. In the words of the Keck Observatory's lead scientist, Andrea was the one that had the crazy idea that there was a black hole in the middle of the Milky Way, and she was determined to prove it. She has also received the Crawford Prize in Astronomy from the Royal Swedish Academy of Science. Andrea is the first woman to receive a Crawford Prize in any field, the Bakarian Medal from the Royal Society of London, a MacArthur Fellowship election to the National Academy of Sciences, the American Academy of the Arts and Sciences, and the American Philosophical Society. Her work of 25 years on the orbits of stars at the center of the Milky Way has opened a new approach to studying black holes. And her group is currently focused on using this approach to understand the physics of gravity near a black hole and the role that black holes play in the formation and evolution of galaxies. Advantages in high-resolution imaging technology enable Gez's work, and her group continues to work on pushing the frontiers of these technologies forward. She serves on several leadership committees for the W.M. Keck Observatory in Hawaii, which hosts the two largest telescopes in the world and the future 30-meter telescope. Andrea is also very committed to the communication of science to the general public and inspiring young girls into science. To honor Andrea, we have invited some gems. Gems are girls in engineering, mathematics, and science who are seriously committed to science. From Palos Verdes High School, Sarah Dawes, who won an award for her outstanding science project. Is Sarah here?
Yeah, I'm here.
So say hello.
Hello. Hello, Dr. Ghez.
And Vanessa, and from Cabrillo High School in Long Beach, Vanessa Patino. Say hello, Vanessa.
Hello, everyone.
And from the state of Maine, Sophia Schumann, our longest attendee for the science pubs. Sophia has been attending these pubs for the last 6 years. She is currently a 9th grader at the Commonwealth School in Boston. Thanks all of you for your commitment to science. Dr. Ghez's work can be found in many public outlets, including TED, Nova's Monster of the Milky Way, Discovery Swallowed by a Black Hole, and TED Talk. Dr. Ghez earned her BS from MIT in 1987 and her PhD from Caltech in 1992, and has been on the faculty at UCLA since 1994. I have gathered from my own experience that astronomy is such a fascinating and popular topic. I guess it is like Dr. Rosenberg said, astronomy constantly reminds us of two contradictory things. First, that the universe is infinite and we are of but the tiniest fraction of importance. And second, that life is rare and precious. A home as beautiful and unique as Earth does not come often. We must take care of it and revere it. Happy Earth Day. Dr. Ghez, we are so excited to hear about your fascinating discovery. Take it away. Thank you.
Thank you, Ethel, for that lovely introduction. And thank you, Sophia, Vanessa, and Sarah for saying hello. I'm just delighted to have you join us this afternoon or whatever time zone you happen to be in. So I started this journey into studying black holes, actually when I was an undergrad at MIT, where I had the real privilege of getting involved in research and learning about telescopes as just an amazing device for learning about the universe. So it was that love of telescopes that actually brought me out to California as a graduate student to study at Caltech, which is an institution that has remarkable telescopes. And as I was finishing my PhD, what was coming online was the Keck telescopes. And the Keck telescopes are, sorry, I didn't do that right. The largest telescopes in the world. So as I began my search for jobs, what I wanted more than anything else was to have access to these telescopes. So I consider myself to have what is my dream job at UCLA. So the Keck telescopes are actually co-owned by Caltech and the University of California. And what UCLA did that was so brilliant was to understand that infrared technologies were going to become incredibly important for these telescopes. And the local industry in Los Angeles is chock full of aerospace industry, which played a really important role in the development of infrared detectors. So this vision of how to become an institution that played a leadership role in the observatories was really quite brilliant. So I was hired as part of this initiative, very interested, and I was really interested in developing new techniques for using these telescopes to get to the highest resolution, and I'll talk about that more in a bit, for these telescopes, and doing that in order to understand black holes. So black holes have always fascinated me. They're the things that used to keep me up at night because they just didn't make any sense. So today, black holes drive a lot of the physics and astrophysics frontier because of two primary reasons. One is that black holes provide this opportunity to understand how gravity works. And in fact, while they're both a prediction of Einstein's ideas about how gravity works, and in particular, how space and time become commingled as you get near in the vicinity of these very intense objects. So he predicts that these objects exist in the universe, but their mere existence also points out that we actually don't have the physics to describe these exotic objects. And I'll come back to that in a moment. So from a basic physics point of view, studying black holes is about moving our frontier forward, and in particular, understanding how we make the study of general relativity, so Einstein's ideas of how gravity work, come together with quantum mechanics, which is the description of things that are very small. So black holes are both infinitesimally small and have large gravity. So they confront our lack of understanding of how to make these two fields work together. So that's fundamental physics. From an astrophysical role, so in terms of understanding how the universe works, black holes, and in particular the kinds that I'm going to talk about, which I'm going to call the supermassive black holes. So as you might imagine, they're really big. Today, we have come to understand that supermassive black holes appear to reside at the center of most galaxies and play an incredibly important role in the formation and evolution of galaxies, which are the basic building blocks of our universe. So if we want to understand the origin and evolution of the largest scale things, understanding this coevolution, in particular the feedback that might go on, that appears to go on between the central engine and its host galaxy, is really important. So that's a second aspect of what makes black holes, or the supermassive black holes, really interesting to study. So let's begin by all agreeing on what a black hole is. A black hole is a region of space where the pull of gravity is so intense that nothing can escape it, not even light. So we can't see it directly. There are also objects where gravity has overcome all other known forces, which means that nothing can oppose the force of gravity, which means these objects become infinitesimally small because gravity wins. So if you think about density, which is mass divided by volume, the density goes to infinity. And in physics, anytime something goes to infinity, it's called a singularity. And it's like a giant red arrow that says, you do not have your description of the physical world right here. So presumably there is some scale, or there is some physics that ultimately halts the gravity from collapsing the objects, but we actually don't know what it is today. It turns out there is an abstract size that we can associate with a black hole. It's known as the Schwarzschild radius, after the person who understood the meaning of this scale. It's also known as the event horizon, which has been popularized by Star Trek. So that's the last point at which light can escape from the black hole, which means we can't get any information from inside this point. It's also the point at which gravity wins. So every object actually has a Schwarzschild radius associated with it. And it's the scale that you would have to compress the object in order for gravity to win. So you have a Schwarzschild radius, your pal does, your cell phone does. You just have to think about how to get the object down to the Schwarzschild radius. It turns out it just scales with mass. So it's a super simple relationship. Scales linearly with mass. So if we want to prove that there's a black hole, we have to show that there is some mass inside its Schwarzschild radius. So that is the ultimate proof of a black hole, is showing that there's a lot of mass inside a very small volume. Now, let's think about where we might find such black holes, these exotic objects that have been predicted by Einstein's ideas. And here there are two kinds of black holes that astrophysicists talk about. One are the stellar mass black holes. And in this first example, it's a beautiful example of theory leading observation. So theoretical work predicted the outcome of the formation of very massive stars that are much more massive than the mass of the sun, roughly 30 times the mass of the sun or more, that at the end of their lives, they would become what we call stellar mass black holes. So roughly on the order of 10 times the mass of the sun. So predicted and then demonstrated beautifully through observations. And in fact, the most elegant confirmation in recent years has been through the gravitational wave detection of merging stellar mass black holes. The story that I'd like to focus on, or the kind of black holes that I'm interested in, are the second category. And we call these the supermassive black holes because they're much more massive. They're more, instead of being 10 times the mass of the sun, they're 1,000,000 to 1,000,000,000 times the mass of the sun. And the story here is quite different because they were not predicted theoretically, but rather observations led people to surmise that these kinds of black holes might exist in the universe. And it came from observations of a very particular kind of galaxy. These galaxies are very energetic. Suitingly, they're called active galactic nuclei because their nuclei or centers have show tremendous amount of energy production. So this is a nice example of one of these, what I like to call, they're sort of like the prima donnas of the galaxy world. And they're about 10% of all galaxies. This example shows a galaxy where the stars in the galaxy are confined to the roughly this region around this bright dot. And what caught people's attention are these jets of emission that come just shooting out from their center. And you can measure how much energy is in these jets, and it's tremendous. So that led people to say, well, there has to be some strong central engine and that lives at the center of the galaxy. And what we also see at the center of the galaxy is light that doesn't look like anything that stars or gas under normal conditions emit. So the picture here is that there's a supermassive black hole, that a tremendous amount of matter is falling onto or through that event horizon, or it's just outside the event horizon. I like to think of this as thinking about the supermassive black hole having a giant Thanksgiving feast. And all this phenomena comes from the feasting of the black hole. Because remember, you can't see the black hole itself. This led people roughly half a century ago to suggest that perhaps all galaxies, not just these prima donnas, have supermassive black holes at their centers. So this is an example of a much more ordinary galaxy. It would look a lot like our own galaxy if we could get outside and look back. So galaxies, for the most part, are flattened disk-like structures of stars. And galaxies like our own have these spiral wave patterns, which is actually showing where star formation is happening. We live about halfway out from the center of a galaxy. We think the black holes reside at the center. And you can think of where the sun lives as the suburbs of a big city, and the center of our galaxy as the crowded downtown area. In fact, that analogy works incredibly well because the density of stars goes up as you go to the center. And almost every property you can think of that describes the property of a galaxy becomes much more extreme at the center of the galaxy. So the pace of things goes up, the intensity of things goes up, the crowding goes up as you go to the center of a galaxy. And this is where we suspect that a supermassive black hole might reside, and that unlike the active galactic nuclei, these other galaxies are have black holes that are quiet simply because they're not accreting or dining or feasting on the gas in its environment. So they're basically black holes that you might say are on a diet. Now, if we're going to look for black holes, and we both want to prove that the fundamental question is, do such supermassive black holes exist? And if you want to prove that they exist, our galaxy is certainly the best place to look because it's the closest example of a center of a galaxy that we'll ever have to study. The next closest galaxy is 100 times further away. So because of its proximity, we have the ability to see far more detail. So that's the pro, but the con is that we live within our own galaxy. So remember, galaxies are flattened disk-like structures. This is a photograph that's taken from the side of Mauna Kea. So you can see the plane of the galaxy. This is the through all this, the band of white. This is the Milky Way, and hence the name of our galaxy, the Milky Way. And presumably, so this is the plane of our galaxy. And hopefully you can also notice that not only is there starlight, but there's also a lack of light that runs through the middle of this plane. And that's all the dust that lives or that resides in the plane of our galaxy. Now in Southern California, we understand dust in the atmosphere quite well. That's what produces smog. And it turns out that the dust that creates smog is very similar to the dust in our galaxy. It obscures optical light very effectively. Light that has a wavelength where the wavelength is comparable to the size of the particle is very effectively blocked by the dust in the galaxy. So if we think about optical light, which is where this picture is taken, is what your eye detects, 1 out of every 10 billion photons makes it to from the center of the galaxy to us. So it's really invisible. So you can't do this work at optical wavelengths, which is the traditional wavelength of astronomy. But if you go longward of what your eye detects to the near infrared, which is where your TV remote control works, and specifically most of my work's been done at 2 microns, 1 out of every 10 photons or light packets makes it to us. You can actually see the center of the galaxy. And now you can see the connection with infrared technology and this project. So infrared, the advancements that have been made over the last 30 years in infrared technology has been absolutely central to opening up this this project, as well as another technology, very critical technology that I'll get to in a moment. Now, what we want to show is that there's a lot of mass inside a small volume. And the most direct way we can do that is by looking at the motions of stars. Stars move under the gravitational influence of whatever is inside their orbits for the same reasons that the planets orbit the sun. So each planet in our own solar system, its motion tells you the mass of the sun. That's really all that's inside. That's the dominant mass. And similarly, these stars, the motion of them will tell you what's inside their orbit. Now, it's useful to keep in mind the timescales. So our sun is going around the center of the galaxy, but it's going to take 200 million years to go around. So, and certainly there's a lot of other things other than whatever's at the center inside its orbit. So in order to show that there's a lot of mass inside its Schwarzschild radius, which is the proof of the black hole, you want to see the stars that are as close to the center of the galaxy as possible. Okay, so you need to be able to see tremendous detail. And that's what led that describes to you, or hopefully helps you understand why I really wanted access to the Keck telescopes, or to be able to develop technology on these telescopes. These are the largest telescopes in the world. Each telescope, it has a diameter, a mirror diameter, which is really how we describe the size of telescopes, of 10 meters. And to give you a sense of scale, that's like the width of a tennis court. So these are immense. And it was actually the University of California scientists here who came up with a breakthrough in the technology for building such large telescopes, which is to segment them rather than to build just one big piece of glass. Now, there are two reasons why people love big telescopes, and there are multiple centuries of astronomers wanting ever larger and larger telescopes, starting with Galileo. And one of the reasons is that the larger the telescope is, the fainter the star that you can see, or the galaxy, and things get fainter as you get to more distant objects, because light has a finite speed that allows you to study the early universe. So a lot of astronomy is driven by the desire to see the largest scales, to understand the origin of the universe. And so you need big telescopes for that. It's actually the second campaign promise of large telescopes that is the one that I'm interested in. So the larger the telescope is, the larger the diameter of the mirror, the smaller the scale that one should be able to see. So it improves what's called your angular resolution. And the way I like to describe this is, if you think about the art technique of pointillism, the technique of painting with dots, the closer you get to the painting, the better your ability to resolve the individual dots. So building larger and larger telescopes is like being able to see more and more detail in the universe. Now, that's in principle. And what's been so difficult about achieving the ultimate or theoretical resolution of these gigantic telescopes is the atmosphere. The atmosphere is great for us. It allows us to survive here on Earth, but it is a total headache for people who want to study the universe. Now, the atmosphere is a really local effect, and the effects of the atmosphere are actually, let me just describe what we're looking at here. So these are 5 bright stars that are right at the center of the galaxy, right where we think the black hole resides. If there were no atmosphere, each star would be the size of the smallest structures dancing around, and rock solid. So it's the atmosphere that is making these dance around. So I like to describe these as bug splat patterns. And it's actually quite profound if you think about it. So this is light that's been traveling from the center of the galaxy. It takes this light 26,000 years to get from the center of the galaxy to us. And in the last 30 microseconds, it hits the top of the atmosphere and gets completely distorted. So the challenge is to overcome the blurring effects of the Earth's atmosphere. And there are a couple of ways of thinking about this. The atmosphere you can think of as a river. Think of a river where you want to understand what's at the bottom of a riverbed. Say you want to distinguish the rocks. The moving river makes that riverbed difficult to see. The other way I like to describe it is you can think of the atmosphere as being a circus funhouse mirror that makes you distorted, and that circus funhouse mirror is moving around at a rate of roughly 1,000 times a second. So the job is to undistort what the atmosphere has done. Now, the one solution, of course, is to get above the atmosphere. You don't have to deal with the atmosphere. So that's the solution of Hubble Space Telescope, which has done a brilliant job in the upcoming James Webb Space Telescope. But both of these telescopes, so let's start with Hubble, are much smaller than what we have on the ground. So Hubble is 2.4 meters in diameter, Keck is 10. And the kind of science that I do improves as the diameter of the telescope to the 4th power. So it's not just a factor of 4, but it's a factor of 4 to the 4th power. So that's more than a factor of 100. And as you'll see, you can capitalize that to get even bigger gains. So what I've done is to work on a number of different technologies that allow us to overcome the distorting of effects of the Earth's atmosphere. So in the early days, it was really just modifying existing instruments. It was a very simple technique from a hardware perspective. It forced us to take the kind of data that you were seeing a moment ago, these very short exposures, and then through computational techniques, we would analyze and decouple or deconvolve what the atmosphere was doing versus what the underlying object was doing. That was the first 10 years. It was very it was hardware simple, software complex, and not that expensive on the scale of astronomical instrumentation. But it was pretty simplistic in terms of what we could do. But it's all you could do for the first 10 years, and we were thrilled to do it. It allowed us to get going. Today, there's much more advanced technology that is enabling us to do so much more. And this is actually quite a remarkable story of technology transfer. Turns out it's not just the astronomy community that cares about seeing through the atmosphere. The military community also cares a tremendous amount about seeing both up and down. And so there was a moment in the early 90s that a technology was declassified as the astrophysical community was catching up. There was a sense that there was no need to develop it twice. And of course, so it was declassified. So there was a huge jump forward. This animation shows how it works. You see light bouncing off the primary mirror that we've been talking about, off a secondary mirror, and into an instrument bay, which in this case is behind the primary mirror. A lot of miracles have happened in this animation, like dome walls disappearing, and we're about to do another one, which is the side of the instrument. No, this is called adaptive optics, and the key element in this system is on the top right, and this is called a deformable mirror, where it's a re-imaged, or so you're basically looking at it's like a replicating the primary mirror in a sense, and it's going to try to take out the distorting effects of the Earth's atmosphere. So now we're looking at what's called wave fronts. If there was no problem, each wavefront would be flat. Because of the atmosphere, they look like Pringles potato chips. And the deformable mirror is going to try to take on the opposite shape so that when it's reflected off of it, the wavefronts become flat again. So this is just a remarkable technology that has all sorts of interesting both hardware and software advances necessary to make it work. It has to do the computations very quickly, and the optical element have to move around very quickly. But it really has finally come to become scientifically robust. So this is the technology that we work with for the last 10 years. And in order to tell the deformable mirror how to move, you have to look at something that you think you understand. And to do that, we shine lasers up into the atmosphere. Turns out that there's a very small layer of sodium atoms that's trapped. So the sodium atoms come from meteorites. It's trapped in a 4-kilometer layer. We shine a sodium laser to stimulate those atoms in those sodium atoms. To stimulate those atoms to shine, and we look at that artificial star, we call it a laser guide star, to tell our deformable mirror how to work. So it's a really it's remarkable technology. It's tremendously fun, and it's really opened up the kind of work that we can do tremendously. So just to give you a little bit of a sense, this shows that those same 5 bright stars, if you take a longer exposure than 1/10 of a second, they look like fuzzy blobs. With adaptive optics, we can actually see many stars. And remember, it's the star's motion that are the key to this experiment. And inside this box in the middle is where the black hole resides. So it's the stars inside this box that are the key to this experiment. Although we track thousands of stars, and it's necessary to do so to understand the orbits of things inside this box. You can see without the technology, it looks like a fuzzy blob. With the technology, you can actually see the stars that are there. now I'm going to show you an animation that's 1/4 of that little box. And I love looking at this animation, I have to tell you. Well, actually, it's the Oscars tonight. We're going to talk a lot about movies, but this is my favorite movie. Actually, it might be my second favorite. I'm going to show you my favorite in a moment. And it's my favorite for a number of reasons. And maybe it's worth sharing with you that when I first proposed this work to the Keck Observatory, it was actually turned down. And I have to say, it was an interesting moment because, I thought I had a really good idea. We'd changed the instruments to do it, but the review committee basically said that the technology wouldn't work. Even if it did, we wouldn't see stars and we wouldn't see a move. So it is immensely gratifying to see these animations and to realize, in fact, how successful this project has turned into. And in fact, it has turned out to open more questions and answers. So let me give you a little bit of a roadmap to some of the things that we're seeing in this animation. In the beginning, we could only take images at one wavelength. So if you are followed by an image, in other words, you just see the positions on the plane of the sky, you're traced with the dashed line. So the fact that the technology gets better and you can see fainter stars is why some stars just appear halfway through the animation. It's not that they're getting brighter, it's our ability to see is getting better. In addition to taking images, which just tells us how things move on the plane of the sky, that's just only 2 out of the 3 dimensions of motion. We also take spectra, and spectra disperse the light and allow us to actually measure how things move along our line of sight. So you get the 3rd dimension. And as the technology improves and our instrumentation improves, you can see stars become measurable in this 3rd dimension. And once that happens, they're traced with a solid line. So it has been a really amazing journey, and you can probably find my favorite star in the galaxy. Its name is SO2. And what does SO2 do for us? Well, it allows us to do a much more powerful measure of what is inside its orbit. I actually didn't mention that, in fact, the early technique for doing this that we did in the first 3 to 5 years was just measuring the average motions of stars. There are many stars that contributed. You don't measure individual stars, but you look at it statistically. But in the end, the individual orbits are really the key. So at the outset of this work, we knew that there was 4 million times the mass of the sun inside this enormous ring. And you can see there's stars, there's also other stuff going on in here. So you're nowhere near the Schwarzschild radius. But this experiment has actually shown that 4 million times the mass of the sun is confined within a volume that's a factor of 10 million times smaller. So that moves the case for supermassive black holes from a possibility to a certainty, because we've now got this 4 million times the mass of the sun confined to a region that corresponds to roughly the size of our solar system. So it's the enhancement of the inferred density that's the key. So the beginning of the work, the first 5 years where you just measure the average motions of stars, got us a factor of 1,000 times better. And then the individual orbits got us the next 10,000 times advancement. And, a factor of being able to move our understanding of something by a factor of 10 million is a rather radical advancement. So if you think about anything in your life that you would like more of, consider getting 10 million times more of it. So today, I know, it's I really don't think we're going to make any next step that's really going to change the evidence for a supermassive black hole. So the focus of the remaining work that we are doing, or not the remaining work, but the work that we're doing now and really excited about, is about using the center of our galaxy as a laboratory for understanding both the physics and astrophysics of black holes. And to illustrate this, I'll show you what is actually my favorite movie. And it's the three-dimensional depiction of how these stars move. And I have to apologize, there's some haltingness that really isn't in this animation. This is just a problem that I'm having with my computer in displaying this movie. Now it's quite big. It's got a lot of information coded in here. And one of the things that it shows is what kinds of stars we find in the vicinity of the black hole. So we're no longer thinking of these stars as test particles to understand the existence or proving the black hole, but we're now looking at the predictions for what should reside around the black hole. And this has been just one of the most delightful parts of working on what I would call technology-enabled discovery, which is by improving our ability to see this region of our universe, we're able to not only answer the questions that we set out to answer, but we've uncovered many more questions and answers. So almost every prediction for what we should see near the supermassive black hole has been inconsistent with the observations. So for me as a scientist, this is like being a kid in a candy shop. There's so much more to understand. So to give you just a brief sense of what's going on, one of the first mysteries that we uncovered are associated with the young stars. So the prediction for the young stars, and by young, I mean a few million years old. And if you anthropomorphize stars, a few million years is like the human gestation period. So this is really, think like infant baby stars. And to get star formation to go, the model that we have is that you take a big ball of gas and dust and it collapses under its own self-gravity. But that's a very fragile starting point. And if you put something like that near a black hole, what a black hole does is it tears, or actually what we call it is spaghettification, spaghettifies this cloud, so it tears it apart. So the prediction is that there should be no young stars in this inhospitable region. And yet the dominant thing we do see in this region are the young stars. Those are the blue-green stars that you're seeing here. So they dominate what we can see today at the center of the galaxy. And an important clue has emerged in measuring their orbits. So the orbits that we were looking at before are really just in the central region, but you'll see just about this point in the pullback is that there's a plane, an orbital plane, which suggests that there may have been a plane of gas that led to the formation of these young stars. So that's just one of many hypotheses, ideas that have been put forward for how to get star formation to happen in this extreme environment. The other two that are depicted here that are really fascinating is that a prediction number 2 for the old stars is that the old stars have had a lot of time to interact with stars, the local stars, and the tendency is going to be for these old stars to congregate around the most massive object in the system, which is the supermassive black hole. So there should be an entourage of old stars around the supermassive black hole. Now the old stars are color-coded orange here, so there's actually a dearth of old stars. So again, it leaves us scratching our heads for an explanation. And again, there's been a lot of theoretical work now that's been driven by these observations to explain a phenomena that we take advantage of in trying to find supermassive black holes in other galaxies, because you look for a concentration of light associated with these old stars. Okay, so in the last paradox that I'll share with you are the pink stars, the magenta stars. These are the first cases of stars that you can see to spatially resolve them being torn apart by the black hole. In order for that to happen, these objects have to be 100 times larger than any star that we predicted. So in other words, this was not something that we had any anticipation of, and yet we definitely see these objects that evolve. So they come in toward the black hole and they become elongated, and then they become more compact as they pass out the other side. Today, my favorite explanation, although I think we have a lot more work to do to nail down that this is actually what's going on, is that these are objects which were originally pairs of stars. And in fact, most stars we think are formed as twins with a companion, and that the black hole has driven that pair of star to merge. And for a very long, for roughly 10 to the 5th years, so 100,000 years, that star will stay, the merger product will be incredibly big. It'll be 100 times larger than a typical star. So it'll have the properties, the characteristics that are necessary to explain these tidal interactions, and may explain other mysteries that have been seen by LIGO, the gravitational wave detections, which also sees a different kind of mergers. In that case, they're seeing stellar mass black holes that are much larger than expected and happening much more frequently. So we may be lighting up a process that will help another community of scientists decode what they're seeing. Okay, let me just skip over to say the other piece that is particularly fun is to look at how gravity works. And today, to get a seat at the table to do this kind of work, you need to see a complete orbit. And there are 2 tests that we can make today. And let me just leave you with the thought that one works and one is not working. And again, to me, when things don't work, is for a scientist, like me, is the most interesting moment. It's when you really have to scratch your head and ask, well, how is it that I can put all this information together? I'm just going to skip over these slides. We can go back and look at them if you want. To move forward with all these mysteries associated with how gravity works near a supermassive black hole and these unexpected observations in the stellar population, the environment around the black hole, technology is key. Today, we're only seeing the tip of the iceberg. We only see the brightest stars at the center of the galaxy. And while they're incredibly powerful, it's very difficult to get the full picture. It would be like trying to understand the stock market by only looking at the largest scale transactions and missing all the small scale transactions. To see the remaining stars, the much more numerous but much fainter stars, you need to improve your ability to see. Today, we use just one laser, and that only corrects actually about 30% of the light into what we call a diffraction limited core. And that's because that laser star is only at 90 kilometers. So if you think about a star coming down, light coming down to your telescope, that's like a cone compared to the starlight, which is coming down in a cylinder. So we call this the cone effect. There's some light that you miss. So the way you get around this is by launching multiple lasers. So we're building a new system today where we will launch multiple lasers to do effectively a CAT scan on the atmosphere to get that full understanding of what's going on in the atmosphere. And if you think about what happens to that problem as you go to larger and larger telescopes, which astronomers are always driven to. So there's a huge project that I've been participating in for the last 20 years. It's called the 30-meter telescope. And as you might imagine, the diameter of this telescope's mirror is 30 meters. There are 3 such telescopes in the world. So actually, Harvard is part of the Giant Magellan Telescope, which is the other. So there are 3 of them, and there are 2 with US participation. So the TMT, which is what UC is part of, and then the GMT, which is what Harvard's part of. And these telescopes are enormous. But this problem of what's known as the cone effect becomes even more dramatic. So in fact, preparing for these telescopes through the advancements of these technologies is essential for not only understanding what's going on at the center of the galaxy. So on the left is what we have with Keck today. In the middle, it's this new technology, multiple lasers, Keck tomorrow. And on the right, it's what this new technology on this next generation of telescopes, either TMT or GMT, would look like. So presumably, we would actually, one would anticipate that you could finally see a star like our sun at the center of the galaxy, which is not possible today. So I want to end with saying this has been an incredible journey of 25 years to keep a collaboration going, both in terms of the people. So I've had the real pleasure of collaborating with two other scientists, Mark Morris and Eric Becklin. This was the original team. On the right is my very, very first grad student, Beth Klein. Today, we're a much larger group. There's a core collaboration of about 30 people and an extended collaboration of about 100 scientists, as this program has become a key science case or program for the development of instrumentation, both on the Keck Observatory as well as the 30-meter telescope. And these students go off and do all sorts of things. They quite frequently go into big data analytics, because our data sets are very big and complex. They often go into actually, they've gone off into the finance industry because the analysis of timing data actually has some interesting connections with the financial market. They go into the military. All the orbital work and the imaging processes that we do are incredibly applicable. So the students are well trained not only to become astronomers, but also to become key members of other industries. So let me leave you with the final comment that I hope, if nothing else, I've convinced you that there's a supermassive black hole at the center of our galaxy, and that by developing new ways of seeing, we've uncovered more questions than answers. Thanks for your attention.
You guys can welcome to clap. I guess I raised your hand, I'm not sure. So thank you very much, Andrea, for your very nice presentation. We have a number of questions, both on the Q&A panels and the chat window. I would like to moderate these questions, and I would like to start with a question by a very smart 6th grader. His name is Zane, and he asks, what happens to all the mass that falls into the black hole? Does the black hole just keeps getting bigger? Do black holes eventually pop or get destroyed somehow? I thought that was very interesting.
Okay, so let's see. I'm making the mistake of looking at the Q&A. So the question was on super black holes. Do they just appear?
No. Do they keep getting bigger? And what happens to them at the end? Do they pop, or do they get destroyed, or what happens to them?
Okay, so supermassive black holes are definitely growing over time, and we think that they grow in concert with the galaxy. So in fact, while it used to be, the question used to be which came first, the supermassive black hole or the galaxy. Today, we understand that that's the wrong way of thinking about it, because the supermassive black hole seems to be always about 0.1% of the central component of the galaxy. What that tells you is that as the galaxy grows, so does the supermassive black hole. So there's some feedback, which is what's exciting to look at. Now, the rate at which these things grow is very, very slow. So I think in terms of understanding the evolution, they're not changing their mass a lot. And in terms of the ultimate evolution of black holes, they're the longest lasting entities in our universe. So there's a wonderful book written by Fred Adams called The Dark Ages. He sort of runs the universe out to its absurd limits, like 10 to the 38 years. It's a very dark and bleak place, but black holes are the ultimate survivors. Wow. in this universe.
Okay, but that means in particular, they grow very slowly, so they're not going to be swallowing that one in the middle of the galaxy is not going to be swallowing us anytime soon.
No, we are safe. So while I have to say black holes have a really bad name as like the cosmic vacuum cleaners, it's a misrepresentation because things happily orbit. So in fact, most of those stars that we were observing in that animation will happily orbit the center of the galaxy without falling in. The rate at which stars are swallowed by the black hole or disrupted by the black hole is roughly once every 10,000 years. So we are in the safety, we're way out in the outskirts of the galaxy. We have nothing to worry about in terms of this supermassive black hole.
Okay, there's a couple of questions, one in the chat window, one in the Q&A, about the James Webb Telescope. Will it be used to further the understanding of the star types around supermassive black holes, and does the infrared temperature sensing will it be used in the James Webb telescopes as well?
So James Webb was going to be super exciting. In fact, it's the proposals for the first round has just gone out. In fact, our group has proposed and gotten time to study the center of the galaxy. And where it benefits us is in the much larger scale. So the center of the galaxy, if you think about the idea that the number of stars, the density of stars goes up as you go towards the center, that means you need better, higher resolution to see the closest stars. But as you get out, smaller telescopes can do a really great job. So we're using this, the James Webb, to sort of understand what goes on around the field that we can really understand in great detail with the Keck telescope. Infrared detectors could definitely advance our research. It's that's the second part of that question. So one of the key things about infrared detectors is they're noisy compared to their optical counterparts. So further advancements in infrared detectors is actually key both as the science detector and as the technology components for adaptive optics.
I had heard about the James Webb. One of the big accomplishments it does is it moves to more infrared sensing than the Hubble does, and I didn't understand why that was so important. I think I really got it from your talk, that it sounds like if you look at things that are really far away, the visible light spectrum just doesn't come to us. They just die off, and whereas the infrared light does get here much more. Is that
well at the center of the galaxy? So what's so the effects of dust. So anything that's dusty, you're better off in the infrared because the infrared light can penetrate the dust. And it turns out that both at the beginning of stars' life, they tend to be embedded in very dusty regions. So if you want to understand star formation, infrared technology is key. And also at the end of stars' life, they tend to have explosions or winds, and that produces a lot of dust in the environment. The other thing that infrared detectors are really good at is understanding anything that's cold. So the colder an object is, the more you can think of the spectrum of light as being there's a peak wavelength, and that's inversely proportional to the temperature. So the colder something is, the longer the wavelength that you want to look at it. So if you want to do direct detections of the emission from a planet, infrared technology is essential. And the lowest mass stars, the coolest stars.
It looks like infrared is the way to go in the future, huh? Because
this is why I think UCLA was so smart.
That's great. Alan Shimon is asking, this is Sophia's father, where do you see the next horizon in this field of research for the next generation of young scientists?
Actually, that was my question.
All right, Sophia.
That was your question, Sophia. Okay, good.
One of the things that's so fun about astronomy and astrophysics is it's a field that's just booming, and it's booming because technology is moving so rapidly. You know, our ability to see and understand the universe it's just exploding. So it's not only these big, so, I care a lot about the big telescopes. So that's going to be one avenue that's just going to be super exciting. But we're also at this moment where we're making the first detections from gravitational waves. And that's a whole other view on the universe. And it was a technology that was developed for 40 years. And all of a sudden, we've gotten to the point technologically where this is possible. So that's super exciting. Today, those instruments are ground-based. So there's a detector in Washington State and Louisiana. And that separation of those, or the scale of those instruments, allows you to study stellar mass black holes. But if you want to study supermassive black holes, it turns out you have to get the scale bigger. So there's a project called LISA that's under development by NASA, which will be a space-based mission. So that'll be extraordinary, and it will open up a new angle to supermassive black holes, and equivalent. It's just, and there are advances in radio. So is yet another domain that holds a lot of promise in astrophysics. So I'd say thanks to just incredible technical innovations that come from a lot of different fields. There's a lot of crossover with the military development that then feeds the scientific inquiry in astrophysics. So I think we're really fortunate.
You described a picture where, I guess in astrophysics, where you have all this experimental data that's inconsistent with predictions that have been made. That's like a complete opposite of particle physics, where particle physics people are just struggling to do any experiment that's not predicted by the theory, right? So that sounds very exciting and very promising for the future. Steve Cooperman just had a comment. Mostly women in the Keck group. He saw a lot of women in the photos. That's very cool. Excellent role model. That's wonderful.
I'll just comment that I think it's a real, I've always been really interested in encouraging women into science, but I've found it that the best way to do that is just by sharing the science. So it's not something that I actively do in terms of recruiting people into my group, because I find that people have to want to be there. So you really want to, work with the students who come to you and express excitement. But it is interesting to me to look today at the group and realize the diversity of the group.
I noticed in the field of planetary science, like all these planets that are being discovered now outside of the solar system, that the people that are making the most impact are very young, and a lot of them are women. Same thing, right? Like, because you have all these like stodgy astronomy, and then suddenly you have all these new ideas coming in, and there's a lot of women astronomers, so they're really making an impact in this field. Let's see. So Art Benjamin is asking, are the non-elliptical stellar orbits near a supermassive black hole due to multiple stellar interactions in the higher stellar density near the black hole?
Oh, that's an interesting question. So today, we actually model all the stellar orbits as elliptical orbits. And they don't look elliptical because, at least in that two-dimensional depiction, because you're seeing things in projection. So so if you think about three-dimensional ellipses, they have some funny properties when you project them. We are starting to look for the deviations from Keplerian orbits, and in fact, that is one of the things that's really exciting about looking for what's called the precession of the periaps, which is what's predicted by Einstein in terms of the orbits that are super close. And one of the things that's most surprising is that star SO2 is actually, it looks like it's precessing in the opposite direction of what Einstein predicts. And that could be from the presence of stellar mass black holes inside SO2's orbits. So it's not quite I mean, yeah. it's not quite the interactions that is being suggested here, but it would be interesting to think further about that.
That was an interesting analogy with the suburbs and downtown and the center of the galaxy. So why would the black hole in the middle be? Would it be like a Skid Row, or why would it be in the downtown LA?
Well, LA has no downtown, so we're really, what do they say, 40 suburbs in search of a city?
Anyway.
I don't know. It's Rockefeller Center, maybe in New York.
Lynette is asking a question. Thank you for your excellent lecture. In the bigger picture, what do you surmise is the origin of the mass, matter, and space of our universe? Is the Big Bang theory on an expanding and contracting universe still applicable? If not, what?
Let's see. So the question is about the universe, the expansion of the universe.
Yes.
Okay, so this is another field that has a subfield in astrophysics that is super interesting. So when I first started teaching at UCLA, the picture we had is currently the universe is expanding, and the question was, would it continue to expand, or would it come back and do the big crunch? And observations in the last, I don't know, decade or so has suggested that the universe is actually accelerating. So it's a really new understanding of what the universe might or might not do. But actually, to come back to the infrared, it's this idea of what the distant universe is doing is based on what we call the brightness of what's known as supernova, so exploding massive stars. And we calibrate how far they are away, or how far we think they are away from local observations. But if you don't understand the effects of dust, all the stuff that we've been talking about in the early universe, you can miscalibrate this largest scale. So there's a lot of work being done today on making sure that we understand how we extrapolate from the local universe to the most distant scales.
I have a related question to the comment about the future for the next generation of scientists. What do you suggest a young person such as Sophia or Vanessa to do? What would be a good habit or a good activity to do now in their 9th grade or 10th grade or very beginning that can help them become a strong scientist in the future?
Oh, I think one of the things to get in the habit of doing is really exploring the things that you enjoy doing, really, and to continue to take risks to expand your understanding of what you might enjoy. The advice I like to give is to encourage people or younger people to check in with themselves every 4 or 5 years on 3 fronts. And when you're young, there's a very natural progression of that, right? When you finish high school, when you finish college, there's kind of that cadence. And to ask yourself 3 things: what is it that you really love? To really be authentic to yourself, as opposed to the boxes that we can put ourselves in. 2, what is it that you can do to expand your understanding, like to take some risk and expand your horizons? Because you don't know what you're going to like until you take that push yourself to take a risk and see what the world might hold. And then the last one is, how can you give back? How can you help other people on that path to understanding how they can make their own authentic contributions?
Okay, great. I'm not sure if you mentioned this, but I was having the question during your talk. Now we have strong evidence of the black hole in the center of our galaxy. So how prevalent do you think these black holes are in the center of other galaxies, the supermassive black holes?
I think the conclusion that we can make is that most, if not all, galaxies have supermassive black holes at their centers. Our galaxy is an ordinary garden variety galaxy, nothing special about us. And every other galaxy that we've been able to explore, while not as, we can't do it at the level that we can do here, nonetheless, it supports the idea that there are supermassive black holes as an important component of both the formation and evolution process.
Mhm. You mentioned this feedback in one of your first answers. There's as the galaxy grows, the black hole grows. What could be this feedback? I mean, how can the two of them talk and communicate in that way?
Well, okay, so one of the super interesting parts about the young stars perhaps residing in a disk. So there's a way of connecting this. So if you the current picture for how active galactic nuclei accrete, in other words, have that light that looks like a Thanksgiving feast, and then produce the jets, is through what's called an accretion disk. So it's primarily fed through a very dense disk, really close in, that feeds the black hole. So it's really interesting to think that because you really need something dense gas in the to allow star formation to proceed. So the fact that those young stars at the center of the galaxy are in a disk suggests that our galaxy had a dense disk that could both form the stars and could have fed the black hole. So that's how you get both a connection between star formation and the feeding of the black hole through the disk. And then once those stars become massive enough, or sorry, evolved enough, they have intense winds and will shut off both the star formation and black hole accretion process. So it's thought to be a cycle of star formation and black hole accretion that corresponds to the life cycle of stars, if that makes sense. And there's some evidence that might happen, because if you look in our galaxy, when the black hole gets active, it emits a lot of X-rays. So you can actually see what we call X-ray light echoes off of clouds that are far enough away that we can associate a time scale with the last time like there was an accretion event. Anyway, that's probably too much information, but we do make that's how we currently couple the star formation or the buildup of galaxies with the buildup of the black hole.
Got it. All right. Well, listen. So this has been very very informative for us. There's lots of questions, but I want to be respectful of the time. I will ask you one last question in the words of Taiwu Young. He says, "Hi, my name is Taiwu, and I'm a 6th grader. A question I have is the universe infinite? And if it is there infinite black holes?"
Yes. And we want you to give us a more detailed answer when you get older.
It's up to you, Taiwu.
Herman, can we finish with Anu's question, please?
Oh, yes. Is it in the chat? Oh, okay. Anu asks, what happens to entropy in a black hole?
I'm going to answer with, I don't know.
All right. Okay, everybody. Thank you for joining us, and thank you very much to Andrea for her time and for your presentation. And we'll look forward to seeing you guys at our next Science Pub.